Okay, so electromotive force and circuits is our next topic. It's the final building block here for our circuits, and it's this voltage that we've only kind of alluded to a few times, not really built up in formal. So electromotive force and circuits, bringing it all together. Okay, so the final piece of the circuit puzzle is to connect this line of conductive material together into a loop or circuit, right? So things have to be connected to a loop. Thinking back to this water analogy, if you let this run until all the water here was depleted, then it's done, right? But if instead you had a pump that pumped the water back up, now you have a continuous flow. And it turns out for electric circuits, it requires that complete connection, that pump, in order to flow at all. It would flow a little bit, but because of the way charges work, if you think about it, the more positive charges you build up down here, the less that positive charges want to flow down towards it because they're repelled by the positive charges. And so if you didn't have it connected in a loop, you would experience some current for just like, I don't know, a microsecond, but it would quickly come to a halt because the charges would repel each other. You need a way for these positive charges to get kicked out of that lower reservoir and come back to the top. And so that is what is accomplished when you have a circuit, right? Usually a little bit neater than that. So the reason we need, let's see, I already talked about that. The reason that the charges need to go back up to the top. Okay, so what is this electrical pump? What is this mechanism that brings things back up to a higher potential, right? We know that voltage is potential difference, the height difference, electrical height difference, right? But what brings things to a high potential in the first place in order to flow downhill, and what brings them from this lower part back up to the top? Well, that is called an electromotive force. So I wrote it right here. Electromotive force, it's often abbreviated EMF, electromotive force. But this is kind of a bad name, and I always like to point these out because I hate when physics education is riddled with these terrible names because it throws you off. So there's really no force about it. So it's not actually a force. It's another energy per unit charge quantity, just like potential. So oftentimes these things were given names before physicists fully understood, everything about it, and so they had like some kind of notion towards what they kind of felt like it was acting like, and some guy along the way just gave it the name force, and now we use that still. Don't know why. But you'll see that everywhere, EMF, and it's abbreviated with this kind of a cursive E there sometimes as well. So because it has the same units as for potential, the SI unit of EMF is the same as for potential, the volt. SI is the volt. All right. So a AA battery, and I suppose they went with A for battery designation because the letter B would be even more awkward. A BB battery has an EMF of 1.5 volts. A AA battery has 1.5 volts contained in it, which means that it does 1.5 joules of work on every coulomb of charge that passes through it. And let me circle right back to that sentence that I just said, because I have to be careful the way that I say things. It has 1.5 volts in it is kind of a bad way to say it, because it's not like, it does have some finite charge separation in it to cause this potential difference, but it supplies a constant 1.5 volts. It's not like something that's like used up. The voltage is that potential difference, right? So a AA battery has 1.5 volts of of height difference, electrical height difference. So it supplies that amount of hill if you connect it to a circuit for the charges to roll down. That's the purpose of a battery, of an EMF, of which a battery is just one example. All right, so other examples of EMF include electric generators, solar cells, fuel cells. There's lots of things. So you've seen me draw these kinds of loops here, and it turns out there's a nice kind of symbolic way of describing circuits and circuit components. So a line, right, is just a wire, so that's what this is, connected in a loop. Some conductor with negligible resistance. A resistor is often denoted with this little squiggly kind of a thing, and you'll see an R next to it usually. So that is a resistor, and this is just wire. A source of EMF is denoted with the symbol like this. So one line is purposefully longer than the other. Sometimes you'll see a little cursive E there to remind you that it's an EMF. And the longer line always designates the positive, but oftentimes you'll see positive charges written on there, at least for our class. And so that means like two terminals of the battery, right? So in real life, this would be a battery that looks like this, and wires connected to the battery like this being the positive side, this being the negative side. The battery is an example of a source of EMF. There's two additional symbols for measuring devices that don't seem like they have a place here, but they really, really do. And so here, I'm going to delete that because it's not a symbol. There's the voltmeter, so something that measures the potential difference or the voltage, voltmeter, and it's designated with the V in a circle. And there's an ammeter, which measures the current, or amps. It's for some reason not an amp meter, maybe because it's just kind of hard to say, but it's designated with an A with a circle around it. And so that measures the current through it.